Hey, welcome back. We're now going to talk about Charles's law. Jacques-Charles was a Frenchman, and he found that the volume of any gas doubled when the temperature increased from 0 to 273 at constant pressure. And as that doubled, he actually measured it incrementally, and he found that for every Celsius degree in temperature that the temperature was raised, the volume also was raised by 1/273 of that initial temperature of 0 Celsius. Similarly, he found, and this should make sense, that the gas would decrease by 1/273 every time the temperature was dropped a degree. Now this would suggest something very interesting. At -273, what would the volume of a gas be? Well, if it continues to drop by 1/273 from its 0 degrees Celsius volume, what will the volume be at -273? It suggests the volume of a gas would be 0. However, what happens to all gases before they become that cold? They become liquids and solids. So the gas law falls apart at that point. But theoretically, if it remained a gas, its volume would drop to 0. Now, Charles' experiments led to the formation of the Kelvin temperature scale that we talked about at the beginning of this chapter on gas laws. Now, the 0 point of this temperature scale is called absolute zero. Now, we're going to do a lab in this class where we will actually find the value of absolute zero. Let me quickly go over some of the details of that lab. At room temperature, which we'll say is about 25 degrees Celsius, we could find the volume of a gas. And then if we cooled that down to 0 degrees Celsius, according to Jacques-Charles, the volume would drop. Right? The kinetic energy of the molecules is decreasing. They can come closer together, so the volume drops as it cools. Now, of course, in the classroom, we're only going to be able to get to a few degrees below 0 if we use ice water. So, we will draw a graph and we will have this portion of it. And then we will extrapolate what will happen if it were allowed to cool to -273. And according to Jacques-Charles, if we're able to cool to -273, the volume in cubic centimeters of that gas would be absolutely 0. So -273 became known as absolute zero. Now let's state Charles's law in words. His is a bit different than Boyle's law, but you'll notice some similarities. He says for a fixed amount of gas, once again, just like Boyle's law, at constant pressure this time, so this time we're keeping pressure constant, not temperature. The Kelvin temperature, or the absolute temperature as it's sometimes called, and the volume are directly proportional. So compared to Boyle's law, we have a couple of differences here. Here we're keeping pressure constant instead of temperature. And here we're changing the Kelvin temperature and we're seeing its effect on the volume. And this time it's directly proportional. This time, if temperature goes up, volume goes up right along with it. Or, if temperature goes down, volume goes down right along with it. Of course, if I take a balloon and dip it into some liquid nitrogen, the balloon will decrease in volume. It's getting colder. The molecules are getting closer together. Now, we could write that as V equals kT, or V is proportional to the temperature. Or, as maybe you've sometimes seen it, V1 over T1 equals V2 over T2. Let's do a couple of quick examples here. If we have 500 mils of hydrogen at 1 atmosphere pressure and 50 Celsius, what volume will it occupy at 37 degrees Celsius in 1 atmosphere? Notice what's being held constant here. Pressure is being held constant, and the temperature is changing. Now, in order for us to do this, we have to make sure we use the Kelvin temperature scale. So 50 degrees Celsius plus 273 is 323 Kelvin. 37 degrees Celsius plus 273 is 310 Kelvin. So we're going from 323 and we're cooling it off to 310. Now make sure your answer makes sense. If we cool it off, the particles move more slowly, they come closer together, I expect my volume to get smaller. Now, we'll do it two ways again. We'll do a little bit of algebra. Let's try that again. V1 over T1 equals V2 over T2. We're going to solve for V2. So what we have V1, we're going to bring this over to this side, times T2 over T1 should be my volume. So let's find out. We have 500 mils, and my T2, that would be my 310 temperature here, divided by my T1, that would be my 323 temperature here. So I'll have my volume in milliliters. Let's see what that turns out to be. 500.0 times 310 divided by 323 equals, well, looks like we're allowed two sig figs here. We're going to go with 480 milliliters. Now make sure your answer makes sense. It got colder. My volume got smaller. Yes, that makes sense. When it gets colder, the volume of a gas decreases. Now let's do it without algebra. Let's just reason it out. Let's start with the volume that we're given, 500 mils, and let's just decide. 323 to 310, it gets colder. If it gets colder, I expect the volume of a gas to get smaller, so wouldn't I put the smaller number on top? And you'll notice the operation is the same. I'm multiplying by 310 and dividing by 323, so my answer will still be 480 mils. Pretty straightforward. Now, if you listen carefully, I did not say the smaller number always goes on top. I said if you expect the volume to get smaller, then put the smaller number on top. Well, why would you expect the volume to get smaller? Well, that happens when a gas's temperature decreases. All right. Now, we'll wrap this up with something called the combined gas law. This time, both pressure and temperature are changing. And we want to see what effect that has on the volume of the gas. Now, we could do something algebraically. It's P1 V1 over T1 equals P2 V2 over T2. It's called the combined gas law. It's called combined because we're going to be taking both Boyle's law and Charles's law into consideration. We're changing both pressure and temperature on a fixed amount of gas. So how do we handle these? Well, we have 1 liter of a gas at 660 millimeters and 27 Celsius. What will the volume be at standard temperature and pressure? Now, standard temperature and pressure, STP, is what we normally call it, is defined as 760 millimeters of mercury and 0 Celsius. So let's write down what we have here. We have a volume of 1 liter. I'm just going to call that V1. The pressure of that gas is 660 millimeters of mercury, and the temperature of that gas is 27 degrees Celsius. But remember, we need to convert that to Kelvin, so 27 plus 273 is 300 Kelvin. Now I want to solve for V2. I don't know that answer yet. I do know the pressure that I'm looking for will be at 760 millimeters of mercury, and the temperature will be 0 degrees Celsius, which of course is 273 Kelvin. Now we can do this algebraically, and I'll do it both ways for you. Don't I need to solve for V2? So V2 would be equal to P1, V1, bring T2 over to the other side, times T2, divided by T1, and I want to bring P2 over here, and P2. A lot of students don't like that. Why? Well, it involves some algebra. But if you plug in P1 and V1 and multiply it by T2, then divide by T1 and P2, you will magically get your answer. But let's try to reason this out instead. I think it's easier. We'll start with the volume that we know. And I'm going to multiply by 2 fractions this time. Because it's the combined gas law. I'm changing both pressure and temperature. So let's decide what number goes on top in both situations. Pressure goes from 660 to 760. Pressure gets bigger. Now what do I expect to happen to the volume of a gas when pressure increases? That's Boyle's law. That's the inverse relationship. When pressure gets bigger, volume gets smaller. So I'm going to put the smaller number on top of my first fraction. Okay? Now I'm going to handle my temperature change. Remember, I need to use my Kelvin temperatures, not my Celsius. So, here temperature's getting colder. Interesting. Temperature's decreasing. Don't the particles move slower and they can get closer together? Won't the volume of a gas get smaller when the temperature gets smaller? That's Charles's law. So I want to put the smaller number on top again. Now once again, I didn't say I always put the smaller number on top. That only happens when temperature gets smaller and when pressure gets bigger. Alright, so let's see what we end up with here. We have 1 times 660 divided by 760 times 273 and divided by 300. And looks like I'm allowed 2 significant figures here. I get 0.79 liters. Now check that. If you want to do it algebraically, you certainly can, and you should get the same answer. Now, in class, we are going to get together in small groups, and we will be doing some Boyle's law problems, Charles's law problems, and combined law problems. So we're really going to flip the classroom around today, where you're going to watch the video and practice these at home, and then we're going to work on an assignment in class. We're sort of doing things backwards this time. So what I would do if I were you to prepare for class is I would watch this video over again. This is Gas Laws Part 3 on Charles's law, and I would review Boyle's law, Gas Laws Part 2. Alrighty? We'll see you tomorrow.